I'm Matteo Bettini, and today I'm going to present my thesis on transport network design for vehicle routing, results on path addition and capacity reduction. Today we're only going to talk about capacity reduction for time purposes. So, to start off, what is routing? Well, routing is the given multiple users and their desired origin and destination, we want to assign each user to a path from its origin to its destination. And this routing can be of one of two paradigms in the traffic context, and it can be system optimal, in which we want to minimize the total travel time of all the users, or this approach also may disadvantage some users for the system's greater good, and it's also unfair for this exact reason. So the other approach, on the other hand, is user equilibrium, where users are self-interested and interested only in minimizing their own travel time. Therefore, in this formulation, no user can improve his or her travel time by choosing another route. And this is a fair approach because every user that starts from the same origin and arrives at the same destination takes the same time. So, for example, this is what you see when you use a commercial application like Google Maps, the user equilibrium routing. While in robotics, usually it's better to optimize for the system goal. So, well, now that we know what is routing, there is a very famous paradox that is called Braess paradox that is as follows. So this is a simple network with 4 intersections, and we can see that under some conditions that are stated in the paradox, the system optimal flow splits perfectly in the two paths available, and also the user equilibrium paths are the same. But if we add this edge over here, which corresponds to a road, under certain cost conditions, some users routed according to user equilibrium will be tricked into taking that path, which is actually not good for the system. Therefore, after the road addition, the total travel time increases for the user equilibrium routing. And this is really important because it tells us two things. First, extreme care has to be used when adding paths to transport network, because we can see, as we can see before, the adding paths can increase the total travel time. And this motivates the first part of our project, which explores path additions problem, which we're not going to see in these presentations. And the other one is that routing can improve by removing infrastructure, because if you have a network, we can imagine that by removing certain roads, we can improve the actual total travel time. So in the literature, people have looked at, given a full network, can we find a sub-network that has optimal travel time? And they do this by removing entire roads, like in the Braess paradox case. But what we're looking into this is bringing this to the continuous domain, and instead of removing entire roads, reducing their capacities in a continuous way. You can think of the capacity as a road as the number of vehicles that it can sustain at the same time. For example, a highway has a high capacity, while a suburban road has a lower capacity. So we want to decrease this capacity, and the case where the capacity is 0 actually corresponds to the whole removal of the road. So then we do this, and we call this task the transport network design problem. So we want to obtain system optimal performance, but we don't want the unfairness of system optimal routing. In fact, we don't want to modify the routing paradigm. So we will keep user equilibrium routing. So how can we do it? We can push users on optimal paths by optimizing the transport network. And this is really important because we can do this just by removing infrastructure. We are not modifying the physical network, we are not adding infrastructure, we are just simulating removal of infrastructure in this project. So how does this look? This is a bi-level game, and it's called a Stockenberg game in game theory because the upper level, which is the network designer agent, can indirectly influence the users, which are the lower level, the other agent, the other player, and it can influence them indirectly through topology modifications, and then the user distribute always according to user equilibrium routing, but according to the new network that has been given to them. So the designer can influence user through these indirect modifications, and this user receive this network and then route, and these modifications we consider them only as virtual. So they are shown only to the users and are not actually physical modifications, and this is a great thing because we can achieve our results without even needing to modify the network. And this bridges a road pricing policy with this network design, because basically what we're doing is we're showing some roads as more congested than they really are. You can imagine it as Google Maps with some of the possible roads, maybe the one that seems the shortest to you, as shown as more congested than it really is by the system, in order to push you to a more optimal road for the system. So we solved this task. We propose one solution that is based on a genetic algorithm. Well, we start with a population of individuals which are all networks with full capacities, and we can see these individuals as these yellow dots. Then every individual is evaluated according to a fitness function, which in this case is the total travel time on the network. So the lowest total travel time will be the fittest network. Then among these individuals we perform crossover, that is every individual is a network and it's actually a vector with all the capacities of the edges. So by doing crossover, mixing these vectors among the fittest, we can get the new generation, and then among this new generation, this is the most important step of our algorithm, and we do mutation, which is a random mutation for each capacity in each network within plus or minus 10% of the original capacity. So we want the capacity to mutate every iteration to get randomness, but not too much, because we cannot remove too much infrastructure, otherwise we know that the solution will always be really bad, because removing in the end tends to become bad if it's not done with conscience. So here is our results. We build a macroscopic traffic simulator in which we import 6 real-world transport networks, which are shown on the table on the left, their dimensions, and on the right you can see the results, where the original is the total travel time of the users according to user equilibrium in the full network, in the original network. Optimal is the total travel time of the users in the original network but routed according to system optimal, and this is the upper bound on the optimal solution that we want to find, because we want to find a solution that is the users still use user equilibrium routing, but we modify the capacities. So we know that we at best we can obtain we can aspire to obtain the system optimal routing performance, but we're not sure that we can, because we're just modifying the environment, we are not modifying the routing. And as we can see on 3 of these networks, we are able to actually go very close to this upper bound on the optimal, and showing that really good results can be achieved. And to make an example, for example, for the Chicago network, where we can achieve 7% improvement in the best case, we are actually able to save 480 routing hours per each traffic hour. That is, for each hour in the city where traffic is going through, we are able to save 480 traffic hours, which is a significant amount, considering that we're only removing infrastructure, and actually not removing it but simulating the removal of infrastructure. So very briefly, we tried to also use for the upper level designer, instead of using a genetic algorithm approach, we tried to use a reinforcement learning agent trained with proximal policy optimization and with this architecture that I'm showing here, which basically has the agent has an action for each road that represents the probability of that action represents the probability of increasing or reducing the capacity of the given road, which is a node in the GNN. But this maybe we can go in another time in depth. And this is the upper level of our design task, where now we have a reinforcement learning agent instead of the genetic algorithm. And this reinforcement learning agent has shown in our results to be able to perform optimization of small networks, like for example in the Braess paradox network, but it gets lost in very big large-scale networks that we have seen. So this motivates the new 2 direction. So the first one would be to go next is to explore these hybrid solutions that combine evolutionary computation, that is the genetic algorithm, with reinforcement learning to solve this complex non-convex optimization problem, which is actually the problem that we're looking at right now, but it's also a very big class of problems. And this is motivated by the intuition that learning plus evolution ultimately equals to intelligent. And then is given that the agent is able to optimize a small network, we can think of using multiple agents and tasking each agent with a small district. That is, we can leverage communication between them to coordinate the search space exploration. So yes. So that was it for my talk. Today we have seen in this talk how we can design networks, these Braess free transport networks, through capacity reductions, and for this we use the genetic algorithm that we briefly touched on our reinforcement learning approach. In the thesis you can find the two other tasks as important as this that I was not able to include, which is we are able to theoretically prove the non-supermodularity of total travel time when paths are added to a transport network, both under system optimal routing and under user equilibrium routing, and also we are able to formulate another design task where we construct Braess free transport networks through incremental greedy path additions.